Last time we had introduced this topic of two-dimensional transformations. We will go into details of this topic today. The first two-dimensional transformation is an operation of translation. So, if we have any point xy and that is translated by a vector given by tx ty, then we can say that the transform point x prime y prime will be equal to xy multiplied by xy plus the transformation vector which is tx ty. Okay. So, x prime will be equal to x plus tx and y prime will be equal to y plus ty. This simple translation operation in which all entities will get translated by a uniform vector. Okay, the shape etc. of the entities will be retained. The other operation that we had seen last time was rotation, and we said that in rotation about the origin by an angle theta, any point xy will get transformed to a point in this manner, and we had said that x prime y prime will be equal to xy multiplied by a matrix which is cos theta, sin theta, minus sin theta and cos theta. Okay, so x prime will be equal to xy multiplied by cos theta minus sin theta, which is x prime will be equal to x cos theta minus y sin theta, and y prime will be x sin theta plus y cos theta. Okay, this will be a transform point x prime y prime. Okay, the third transformation that we had seen last time was the scaling operation. And in scaling we had said that x prime y prime will be xy multiplied by a scaling matrix which will be sx0 and 0 sy. Okay, x coordinate will get multiplied by sx, the y coordinate will get multiplied by sy. This is the scaling operation. So, if we have a figure like this, and we scale it by a factor of 2, it will become something like this. Okay, all the x coordinates will get multiplied by 2, the y coordinates will also get multiplied by 2 of all the points. This is the scaling operation. Now let us see reflection. If you have any arbitrary point xy and we reflect it about the y axis, this point will be x prime y prime, which will be nothing but minus x y. Okay, so when you are reflecting about the y axis, the transformation can be written as x prime y prime will be equal to xy multiplied by minus 1 0 0 1. Similarly, if you are reflecting about the x axis, this point will go somewhere down at this location, and the coordinates would then become x minus y, and this matrix will become 1 0 0 minus 1. Okay. Similarly, if you reflect about the origin, that means we take this radial line, proceed it in this direction, and we get a point in that direction which is minus x minus y, and for reflecting about the origin, the transformation matrix will be minus 1 0 0 minus 1. Okay. So when we are reflecting about the y-axis, the x-axis will become the x coordinate will change its sign. When we reflect about the x-axis, the y coordinate will change the sign. When we reflect about the origin, both the coordinates will change the sign. Okay. Now if we compare these matrices with the scaling operations, we notice that for reflecting over the y-axis, it is nothing but the scaling operation with Sx equal to -1 and Sy equal to +1. Okay. Similarly, the other two reflections can also be captured as scaling operations. Okay. So reflection is nothing but a specific case of scaling. Whenever we want to reflect a point or an entity about either the x-axis, y-axis or about the origin, that can always be obtained by scaling by having the correct values of Sx and Sy. Okay, either one or both of them will be -1. Okay, so for the four operations that we have seen, we can summarize in this manner. Translation is captured by x prime y prime is equal to xy plus dx dy. Rotation is captured by x prime y prime is equal to xy multiplied by cos theta sin theta cos theta. Okay, and scaling is captured by the equations okay, and of course reflection is a specific case of scaling. Okay. Now in these three basic operations, if you notice, translation is captured by the addition of two matrices, while both rotation as well as scaling are captured by multiplication of two matrices. Okay, and multiplication is definitely more convenient because let us say if we take any point in this coordinate system, we first want to rotate it about the origin, we get this point, then maybe we want to translate it and go to the third point. We can capture that as a sequence of rotation or sequence of transformation, sorry. We will get point P1 will be equal to the point P multiplied by some transformation matrix T1, where this T1 corresponds to this rotation. Now this point, let us say, is to be scaled. If this point is to be scaled, we will say P2 will be equal to P1 multiplied by some other transformation matrix T2, which is nothing but P into T1 T2. Okay. So if all our matrix, all our transformations are captured as matrix multiplications, the transformations can be very easily, multiple transformations can be very easily captured. Okay. Essentially with this aim, we will define what are called as homogeneous coordinates. In homogeneous coordinates, every point xy will now be written as x multiplied by some number h, y multiplied by some number h and h. Okay, so a point xy, instead of being written as a tuple, will now be written as consisting of three numbers. Okay, so if you have a point, let us say 2 3, this point can be written as 2 3 1. It can also be written as 4 6 2. Okay, it can also be written as 1, 1.5, 0.5. All these represent the same point. Okay. Basically what we'll do is whatever be the value of this homogeneous coordinate, we'll divide both of these by that value. Okay, and then when this value is equal to 1, these two will give us the exact x and y values. Okay, so any point xy can always be represented as xy1. So xy1 is one of the homogeneous coordinate representations of the point xy. Okay, we have basically added one more coordinate to a two-dimensional point, and the advantage is that to start with, if we are talking of translation, earlier we had written x prime y prime is equal to xy plus tx ty. Okay, now x prime y prime will now be written as x prime y prime 1. This will be equal to x y 1, and now since our points consist of 3 coordinates, our transformation matrix will also be a 3 by 3 matrix, and for translation we will get 1 0 0 0 1 0 tx ty 1. Okay, we can say this is h. So x prime will be xy1 multiplied by this column vector of 1 0 2 x, which is nothing but x plus tx. Y prime will be xy1 multiplied by this column vector, which is nothing but y plus ty. Okay, and the homogeneous coordinate h will be just this row vector multiplied by this column vector, and we will get 1. Okay, this way even translation can be captured easily as matrix multiplication. Okay, the other two operations, we are talking of rotation, x prime y prime h will be equal to x y 1 multiplied by, the basic matrix will remain the same, in other places we will just add zeros and ones. Okay, this way x prime will be equal to this row vector multiplied by this column vector, which gives us the same equation as we had earlier. Similarly, y prime will be this row vector multiplied by this column vector, which will again give us the same equation as earlier, and the homogeneous coordinate will just give us 1. Okay, so rotations can also be captured in a similar manner. Then scaling, that can also be captured in a similar manner. And we have to scale by an amount of sx. This row vector will get multiplied with this column vector, and x prime is equal to sx times x, and y prime is equal to sy times y. The homogeneous coordinate h will again be equal to 1. Okay, so this way by using homogeneous coordinates, we are first able to capture translation by this matrix multiplication operation. Okay, and similarly even rotation and scaling are captured as matrix multiplication operations. Okay. Yeah. keeping h equal to 1. Yes.
So use like adding a third parameter instead of making x dash y dash multiplied by x y divide x by 1 upon x.
See, if we divide h by 1 over sx, we'll get uniform scaling in both the directions. Again?
Multiplying by 1 over x.
See, okay, I'll just come to that in a minute. The reason why we've added homogeneous coordinate is the first primary reason is that translation should be captured as matrix multiplication. Okay, if we don't add the homogeneous coordinate, translation will not be captured as a matrix multiplication. Okay, as a result of that, we will not be able to combine different kinds of transformation by a single matrix. Okay, we'll just see how that is to be done. The second thing that you are saying that instead of this 1, if I change this to some value, let's say 1 over s. Okay, if I change it to 1 over s and these for the time being are, let's say, both equal to 1. Now we will get uniform scaling in the x and the y direction. Not different scaling. We will get uniform. Yeah, you won't get different scaling. You will get uniform scaling in the x and the y direction. Okay, this is 1, and this is 1 over s. This point will become x, y and 1 over s, which is identical to x times s, y times s and 1. Okay, so if we want uniform scaling in both the directions, we can just give a 1 over s factor in the bottom right corner of the transformation matrix. Okay, if we want non-uniform scaling, then we need to give one factor over here and one factor over here. Okay, if we want to translate a point, then we need to add some value here and some value here. If we need to rotate a point about the origin, then we'll have some value cos theta here, sin theta here, minus sin theta here and cos theta here. This is when we want to rotate by an angle of theta counterclockwise about the origin. Okay. Now I had mentioned that if you have to combine different operations, different transformations, we can take any point P, transform it by matrix P1 and we get, let's say, the point P1. Okay, we can take this point P1, transform it by another matrix and we'll get P2 will be equal to P times T1 T2. And continue this operation, we'll finally get Pn, which will be P T1 T2 multiplied till Tn. Okay, this means that for transforming any point P, we can take each of these individual transformations, multiply them together, or I can write it like this. I can get one combined transformation matrix for all these transformations. Okay, this we are able to do purely because all the transformations there are represented in the form of matrix multiplications. Okay, we just see one specific example of where this kind of thing is very useful. So far, when you are talking of rotation, we are rotating a point about the origin. Okay, we have taken a point xy and you are rotating it about the origin by an angle of theta. Instead of that, if I have a point xy and I want to rotate it about any arbitrary point AB, Okay. How do I find out the values of x prime and y prime? I know that if I am rotating about the origin, I know what is the transformation matrix meant for that. Okay, if this is the case, I can easily get x prime y prime 1 will be equal to xy 1 multiplied by some transformation matrix meant for rotation. But if I have to rotate about the point AB, how do I find the transformation matrix for this case? Okay, what we will do is we will translate the axis such that AB becomes the origin. Okay, this origin should come to this location. We will then rotate the point xy to x prime y prime, okay, and then we will translate this axis back to this position. Okay, so step 1 would be to translate origin to AB. Okay. Step 2 would be to rotate by theta about origin. Okay, and step 3 would be to translate origin back to its original position. Okay, so for rotating a point about any arbitrary point, that can be done as a sequence of these 3 steps. And how do we translate the origin to the point AB? What will be the transformation matrix for that? Anyone?
Translate all the points to minus a minus b.
We will translate all the points by minus a minus b. Okay, not by AB. So transformation matrix for this will be 1 0 0 0 1 0 minus a minus b 1. Okay, this is the first transformation matrix. T1 will be equal to this. Is that okay? Is this clear as to why we are using minus a and minus b over here? No? Okay. See, what we want is that this point AB should now have the coordinate of 0 0. Okay. So to A and B, I'll have to add minus a and minus b. That means what I'm effectively doing is this point is being translated back to the origin by this amount. The translation vector is minus a minus b, not just AB. Okay. So when you're translating the origin to AB, that is the origin should become this point. That is the coordinates of AB should now become 0 0. That is a negative translation by AB or translation by minus a minus b. Okay. So the first step is we translate the origin to AB using this transformation matrix. Then we have to rotate by theta about the origin. What is the transformation matrix for that? The same as the one for rotation. Cos theta, sin theta 0 minus sin theta cos theta 0 0 0 1. Okay. For rotation about the origin, we will use the same matrix as that is meant for rotation by an angle theta. Then translating the origin back. How do we translate the origin back? Again?
T1 inverse.
the inverse of T1, or that would be AB. Okay, this would be 1 0 0 0 1 0 AB, AB1. Okay, and we want to translate the origin back. Again, this point should retain the coordinate of AB. Okay, the point which was 0 0 should now retain the coordinate of AB. So we will add AB to all the coordinates. Okay, so if we combine these three, our combined transformation matrix will be the product of the three transformation matrices. Okay, or we can also write this as T1, T2 and T1 inverse. Okay, and now if you want to rotate any arbitrary point xy about the point AB, all that we need to do is P prime will be equal to P times T. Is that okay? So this way we can combine any sets of transformations into a single transformation. Okay. Similarly, if we want to we have a point, arbitrary point xy, and we want to reflect it about an inclined axis. How do we reflect a point about the x or the y axis? We use the scaling operations. Okay, now if we want to reflect it about any arbitrary axis. Okay, let's say the axis is passing through the point AB, and has got direction cosines of LM. Okay, how do we reflect the point xy about this axis? Anyone? So first translate we translate the origin to this point, so that this AB now becomes the origin. Okay, so we are translating by a vector of minus A minus B. Okay, then we rotate. Okay, for this we will get some transformation matrix T1. Then we rotate the axis so that this this direction coincides with the, let's say, the x-axis. Okay, that means in the first step my axis has become like this. In the second step I rotate my axis so that my axis becomes like this. Okay, that is rotate. This will give us a transformation matrix T2. Then I will reflect about the x-axis, that will give us a transformation matrix T3, and then I will do the reverse of these two. Okay, so the combined transformation will become T, will be T1, T2, T3, T2 inverse, T1 inverse. Okay, the sequence is important. I cannot take the inverses in the opposite order. Okay, I am doing T1 then T2, so the inverses have to be taken T2 inverse first, then T1 inverse. Okay, any questions on this part? These individual transformation matrices, you should be able to write them on your own. Okay. Transformation matrix for translation, for rotation, for reflection and the reverse of these two transformations. Okay. Only one thing you should be careful about is in step 2, when we are rotating the axis, let's say this angle is an angle theta, we will have to write the transformation matrix for minus theta. Okay, because what we want is that this direction should now become the x-axis. Okay, so a point on this axis will be a point on the x-axis. So this point which was earlier xy should now become, let's say, some x prime 0. Okay, that will be obtained when I am rotating actually by an angle of minus theta. Okay. Similarly, translation, we have done minus a minus v, the rotation will be by minus theta. Okay, reflection in P2 inverse, here we will have rotation by theta and translation by AB. Okay. So, we have basically seen how we can combine different operations and get a combined transformation matrix for a series of operations. Okay. The basic advantage that we have of using homogeneous coordinates, the first advantage was that translation can be captured as matrix multiplication. Okay. The second advantage that we have seen is uniform scaling can be captured by one single parameter. Okay. The third way that we have seen is that transformations can be combined. Okay. One more advantage of using homogeneous coordinates is that if we want to represent a point at infinity, that's infinity in this direction, we can take any point here xy, and xy0 will be a point at infinity in that direction. Okay, because we said that our homogeneous coordinate x, y, h actually corresponds to x by h, y by h and 1. So if this h is equal to 0, this point represents a point at infinity, okay, in the direction of xy. So another advantage of using homogeneous coordinates is points at infinity can be easily captured. Okay. Now in the homogeneous transformation matrix, we've got 9 terms. Okay, I'll just write them as A, B, C. Of these 9, we've seen that this is the homogeneous coordinate. It gives uniform scaling. Okay. These 4 are giving us rotation. These 2, in addition to rotation, they also give us scaling. Okay, and these 2 are giving us translation. So far, these 2 we have retained at 0 for all transformations. We have not tried to modify these 2. Okay, we will see later on that these 2 are used for capturing perspective transformations. You know what is the perspective view? No? And you will see that later. If you want to capture the perspective view of any object, then we will be using these two coordinates to capture the perspective transformation. Okay. So another advantage that we will see of these homogeneous coordinates later on will be perspective transformations can easily be captured, or perspective view can easily be obtained by such transformations. Okay, so these are some of the advantages of using homogeneous coordinates. Okay. Any questions on this part? Okay, then we just extend this idea to transformation in 3 dimensions. So if you have any 3D point, so if you have any 3D point which is x, y, z, again we will directly go into homogeneous coordinates. This will represent as x times h, y times h, z times h, and h. Okay, so this will be a 3D point will be represented as a 4 tuple. Okay, where h is the fourth coordinate will be the homogeneous coordinate. Okay. Translation. I don't think I need to define translation again. The translation matrix will be a 4 by 4 matrix now. Okay, so if we want to translate any point by tx, ty, tz, in the bottom row we will have tx, ty and tz in one place. Okay. Scaling. For scaling we will get sx 0, 0, 0. Okay, 1 by s is for uniform scaling, sx, sy and sz are for non-uniform scaling. Okay. Now let's come to rotation. In the 2-dimensional case we are rotating about a point which was the origin. In a 3-dimensional case we can't rotate about a point, we have to rotate about an axis. Okay. So let's take the first case. We want to rotate about the z axis by an angle theta counterclockwise as we look from the top. Okay. For that, what will be a transformation matrix? X prime, y prime, z prime. These are 3 points. What will be the value of x prime? Our initial point was x, y, z, 1. X prime will be equal to x cos theta minus y sin theta. Y prime will be equal to x sin theta plus y cos theta, and z prime will be the same as z. Okay, the value of z prime will not change since we are rotating about the z axis. Any arbitrary point, let's say here, we are rotating it like this, the z value will remain the same. Okay, so the transformation matrix for this case stands for cos theta, S stands for sin theta. Okay. So this is the transformation matrix for rotating about the z axis. We can write it as Tz by an angle theta. Okay. This is the transformation matrix for this operation. Now if you want to rotate about the x axis, what will be the transformation matrix? For rotation about the x axis by an angle theta, the x coordinate has to remain unchanged. Okay, so this will be 1, 0, 0, 0. These four values we have to fill up. What will they be? Cos, sine, minus sine, cos. Is that okay? I have directly written the result, but it should be quite clear as to how we got this. Okay. I want to rotate by about theta, sorry, about the y axis. The y coordinate will remain unchanged. These four coordinates, these four values will have to fill up. What will these values be? Anyone? C, S, minus S, C. Is that correct? Minus S, C will be above. No. Just think of the figure. Okay, X, Y, Z. Okay, so on this XZ plane, I am drawing the XZ plane now. This is X, this is Z. I am rotating by an angle of theta. This is my point P, this will be my point P prime. The Z value of this point is going to decrease.
Signs will be the negative of each.
So this will be plus, this will be minus. You can verify it from this figure. Okay, the Z value is decreasing, the X value is increasing. Okay, so the X value will be C times cos theta times X plus sin theta times Z. Okay, the Y value will remain unchanged. Okay, so when we want to rotate about the Y axis by an angle theta, this will be the transformation matrix. Okay, so the basic transformations we have seen. So basic transformations were translation, scaling, then rotation about the x axis, sorry, about the z axis, and about the x and the y axis. Okay, now from these basic operations, let's try and get some of the other operations. The first is reflections. Okay, if you want to reflect about the xy plane, what will happen? The z value will become negative. Okay, the rest will remain the same. Okay, similarly, if you want to reflect about the xz plane, the y value will become negative. Okay, so for that 1, minus 1, 1, 1. All the others will be 0. If you want to reflect about the yz plane, we will have minus 1, 1, 1, 1. All the others will be 0. Okay. If you want to reflect about an axis, so if you want to reflect about the x axis, what will happen?
Both y and z values.
Both y and z values will change. Okay. Similarly, if you want to reflect about the y axis, x and z values will change. If you want to reflect about the z axis, x and y values will change. Okay. If you want to reflect about the origin, reflecting about the origin, all the values will change. Okay, so reflections are very easily captured as scaling operations. Okay. Now let's again talk about rotation, or rotation about any arbitrary point or about an arbitrary axis. So we want to rotate about an axis like this. Okay, this is, let's say, the point A, B, C, and this vector has got direction cosines of L, M, N. Okay. How do we rotate about this arbitrary vector? We have any point x, y, z. This is my x axis, this is my y axis, this is my z axis. I want to rotate this point x, y, z about this vector, so we'll get something like this, again by an angle theta. Okay, this will be transformed to some point over here. This is P, this will be transformed to P prime. How do we find out the coordinates of P prime? Okay. What will be the sequence of steps involved? Anyone? We translate so that this becomes the origin. Okay. Translate by minus A, minus B, minus C. So now my axis will look something like this. What is the next step? We rotate so that rotate such that vector element coincides with one axis, any axis, let's say. For the sake of argument, let's just say as with the z axis.
This will take 2 rotations.
This will take 2 rotations. Okay, what will be 2 rotations? We will first rotate so that this vector comes into the xz plane, then we will rotate so that it coincides with the z. This is one matrix P1. This will be 2 rotations, let's say R1 and R2. Okay, then we will carry out the actual rotation. Okay, that let's say is R. Okay, and then we will say reverse of steps, reverse 2 and 1. Okay, whatever transformation is obtained in step 2, we'll do the opposite of that. Whatever transformation is obtained in step 1, we'll do the opposite of that. Okay, the combined transformation will come out to be T1, R1, R2, R, R2 inverse, R1 inverse, T1 inverse. So if you want to rotate point xyz over any arbitrary vector, that will be done by a sequence of these 7 steps. Okay. In the next class, what you will see is how these two rotations are done. What will be the angles and about which axis these two rotations will be done. Okay, we will see that in detail in the next class. Again?
R2 inverse, R1 inverse, T inverse.
Yeah.
So we just do, since we already have this product T1, R1, R2, we take the inverse of just the composite matrix.
Same thing, we will put this as T2 and this will become T2 inverse.
All is T1, R1, R2.
Okay, you take this as, let's say, T2 and then this as T2 inverse.
Yeah.
You can do that, but once you have multiplied the 3 matrices, finding out the inverse is going to be a difficult job.
4 by 4.
4 by 4 matrices, you have to find out the inverse by the matrix inverse algorithm. For each of these individuals, the inverse is just the rotation by an opposite angle of minus theta. So these, this T2 inverse can be found out easily by matrix multiplication. It is easy. Okay, that is why I will prefer to do this kind of thing. Nevertheless, you can multiply them, then find out the inverse, this will get the same result. Okay. Any other questions? Okay.